Hi. Hi, Dr. Xiao.
Hello?
Well, yeah, we can hear you.
Okay, good. That's good.
Good. Can we try share screen first?
Okay. Let me try share the screen.
Yeah.
Let me. Okay. Share screen.
Can you try full screen?
Yeah. Let me try full screen.
Yeah.
Is this good?
Yeah. Can you move your mouse just to see? Yeah. Good.
Yeah. So I can point some things like this.
Yes.
I was trying to use the classical pointer. It's like the laser pointer. Then I realized, oh my goodness, I can, only I can see the points.
Yeah. Can you?
Yeah. So this mouse is better.
Yeah. Can you move around just to? Sure. Yeah. Great. Yeah.
Okay.
Yeah. Great.
Good. Yeah. Let's see. Are you guys all in at your homes, like school?
Home.
No school?
No, we cannot go to school.
So how are you?
Are you? Yeah.
Good. I'm good. Yeah.
By the way, later Joran will introduce you.
Yes. Hi, Professor Xiao.
Hey, Joran.
你
们两个都是卓然的，这个名字是一样啊，昭然和卓然 ，sorry， 昭然和卓然 ，OK， 差一个，我还以为是一样的。
Yeah, yes. I think we've met at some conference in Montreal. I forgot it's whether in Europe or SML.
Montreal. I think Montreal is always in Europe.
Yeah.
So I will first introduce you to the audience, and then you will deliver the talk, and we won't interrupt you during the talk, and we will collect all the questions raised during your talk and pass them to you after the talk.
Okay, so how long is the talk? I should go.
What?
How long should I go for the talk?
About 15 minutes.
Okay,
roughly speaking, 15 minutes, but
okay.
It's not very strict. And
yeah, I should. Yeah, that should be right. Yeah. And without the interruption, I could, better control the pace, I hope. Yeah.
Yeah, yes. So there will be a Q&A section only after the talk, and which, depending on the number of questions, usually it ends in 10 minutes.
Okay. Good.
So in Washington, the COVID now is fine, right?
COVID is well, the first epicenter, right? When it came out, is Washington, the worst place to be. Now it's okay. We're dropped to so low in the 50 state. I think we are kind of I think 20 out of like 20 or 30 place. So it's good. It's much better now.
Yeah.
We don't have many people like there are other big states.
Yeah, our state is fine, but our time is bad nowadays. Today we have 200 new cases. Considering we are a small university town, this is quite scary. Yeah.
Yeah, I think that's when you have a university town.
Yeah.
I think Washington's. I think the whole state is at like that level. It's like 200 or between 200 to 400, something like that.
Yeah, and we only have say 100K people. So, and 200 cases per day is very scary. Yeah.
Let me stop sharing for a little bit. Okay, I will just easily share it.
Sure.
Yeah. Yeah, I heard from like Wisconsin, right? I mean, like they opened the school, and then I don't know, they like have like thousands of confirmed cases.
Yeah, we have about 1,000 now. Yeah.
Yeah, I thought last time we had a meeting with I think Steve Wright and Robert Nowak. They say, oh, they're Wisconsin. They have to shut down for, I don't know. They say it's gonna be stop for a couple of weeks, and they don't know what to do next yet.
Yeah.
Oh, they are not the worst. I think, like, let me see. So far at Georgia Tech, we have 928
Cases?
confirmed cases.
Wow.
Oh,
Wow.
And I think University of Georgia almost doubled.
Yeah, I know. Wisconsin had like
Almost tripled.
no, we had like a 1,700, I guess. That's the number they told me. But they say it's much more than that because it should be many more than that because of the somehow the rain or something like this. They have the result not coming out yet. I mean, it's very hard to stop this, especially for the undergraduate dormitories, those kind of classes, bigger classes. That's very hard to control. Because I see you have very good kind of background pictures of those books.
Yes.
Yeah, my background is.
Is this some park?
No, that's a backyard of Terry Rockefeller.
Oh,
wow.
I see.
Yeah, he has a very good backyard, a very nice backyard. It has like a little paths and waterfalls. It has things.
I see. That looks pretty nice.
He dug the waterfall by himself. It was like there was like a underground creek going through his backyard.
Really?
And he decided to just dig everything out and make some like landscape. Yeah, he's good at this. Of course, this is many years ago.
So where does he live? In Seattle or Bellevue or Redmond?
Which who?
You mean this backyard is in
Seattle? In Seattle.
Seattle, okay.
Yeah, I was looking for background, then I found this one. Looks cool.
Yeah.
So how long you think this this series will go? You will go like go for a whole year?
Yeah, good.
So we have some gift from 2 Sigma, and
Okay.
I think we will like go until the money. So actually we will send you a gift card, and for each speaker. So we'll go until the money runs out.
Okay, that's nice.
Yeah. I think they have plenty of money to support us. I mean, even if the funding was run out, it's not matter.
We can
we can ask for more.
Perhaps.
Yeah. Are they starting some kind of also research lab, right? Not the like a Microsoft or Fair type, but they have their own like kind of research branch, like quants, kind of the finance.
I see.
I heard they are. I think they're reorganizing. Yeah, because I heard that's what I heard. Just not that accurate, but their research department is not making much progress. Or not making profit. That's what I heard.
Yeah.
Yeah, is NeurIPS, the decision still not out yet, right?
No.
Okay, I don't know. I think after this pandemic, so they kind of take it much longer, much more time to do it because no one needs to travel all the kind of things. So I think usually would be have been done very much earlier, the decision.
Right.
When, as you can, is this already open to the?
Yes.
To the chat room. Okay.
Yeah.
So we're already live, right?
I think so. Yeah.
Oh, already live. Okay. Oh, there's already 28 people.
Yeah. Yeah, so we usually start at 3:02 to give attendees 2 minutes to attend.
Okay. Yeah, no worry.
So we just recently changed the regular time slot for the seminar. That's why some people might got confused with the time. Yeah.
Yeah, okay, good. Yeah, I think say now your background is more appropriate. It's like the Illinois, University of Illinois. You have your school background. That's better.
It's all professional, right? Yeah.
I think everyone should have something like this. That'd be really good. Actually good. I mean, we especially for online to seminar, those kind of things. It's better. Yeah, I would consider change to my kind of official background.
And yours is your backyard, I suppose.
So this is a Rockefeller's backyard.
Oh.
Yeah, Neil, actually, I like your the radio thing going out. It looks like a Pokemon and
Oh, okay, really?
about to release your Pikachu.
I should address yellow next time. So I heard there are also some mountain fire smokes at Washington.
Oh yeah, yes, really bad. I mean, actually, really bad. Literally, lots of smokes.
Really?
Yeah, like the air quality. I don't. They have some numbers like way beyond 200 or 300. I don't know. I forgot what this number.
In Seattle area.
Yeah, and also the first time at Seattle, we wanted it to rain. The weather is not cooperating, we just, let's please rain. I mean, at Seattle, you don't really think about it. We don't want rain, but this is the time we really want rain.
I see. So I thought
it's quite surprising.
Yeah, if you look at this fire maps, all of the West Coast from Washington, Oregon, California. I mean, even not West Coast, even like inland, past the mountains. Still, there's like other state. I think maybe I don't know if it's Utah or no, not Utah. No, it's some Colorado. I don't know, like Arizona. So yeah. I think the whole Washington state is like has lots of fires, not only on the coast.
Oh.
So you can smell it.
Yeah. I literally feel like the lung. I literally can feel a difference in the lung.
I see.
When I go outside, I have to change the filters yesterday. I just changed it.
Yeah, sorry to hear that. Yeah.
I think it's still better than California, the area, and LA maybe. Yeah.
Both.
So we don't have fire nearby phi. I think the fires are, we got things from, we do have fire in Olympic National Park, we say, something near there. But
is this the first time you experience this wildfire in Washington after you joined Microsoft?
No, that's the second time. I think like a couple of years ago there was once. There was once, but this time is much longer. I remember that's like 2 days. It's gone, 3 days are gone. But this is like for a week.
I see.
Yeah. So I think yeah, we're gonna have rain in a week at the latest. Yesterday it actually rained, but just not big enough.
Yeah, but I feel the rain in Seattle is more like a drizzle. So probably it's not good enough to stop the fire, right?
Yeah, it's not also just not good enough to clean the air. You know, you just it's drop somewhere, but you leave lots of the kind of the dust in the air still.
Yeah. Yeah, we will start in 1 minute.
Let's get started.
Okay.
So shall we start?
Let me. Okay. Yeah. Okay. I will share screen after you introduce introduction. Yeah.
Oh, sure. Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our distinguished speaker, Dr. Lin Xiao from Microsoft Research. Dr. Xiao is a senior principal researcher at Microsoft Research AI located in Redmond, Washington. Prior to joining Microsoft, he received his PhD from Stanford University and was a postdoc fellow at Caltech before joining Microsoft. He has made fundamental contributions to optimization theory. He currently serves as an associate editor for the SAM Journal on Optimization and has served as area chairs for many machine learning conferences, including NeurIPS and SML. He has won many awards. He was a winner of the Young Researcher competition at the first International Conference on Continuous Optimization in 2004 for his work on fastest mixing Markov chains. And he has won the Test of Time Award at the NeurIPS 2019 for his work on the regularized dual averaging method for sparse stochastic optimization. His current research interests include theory and algorithms for large-scale optimization and machine learning, reinforcement learning, and parallel and distributed computing. Today, Dr. Xiao is going to talk about statistical optimization methods for machine learning. Please join me in welcoming him.
Okay, thank you. Thank you very much for the introduction. Let me share the screen.
Yeah, your screen sharing works very well.
Very well, okay, good. Let me go back to, okay.
We can also see your mouse.
Okay, good. Thank you. I first want to thank the organizer inviting me. I think this is a really great opportunity to speak in this online seminar series. I think also this is a great venue for keep communications and interactions in this quite difficult time. I thank you for the service to the community. Today I'm going to talk about statistical optimization methods for machine learning. So as we all know, statistics and optimization are 2 of the foundational pillars of machine learning. So it is well known that optimization provides powerful tools for statistics. There's also a complementary aspect that are kind of gaining more and more attention in recent years. That is, statistics can help improve optimization algorithms. A archetypical example in this aspect is stochastic gradient descent, which is a powerful optimization algorithm for solving especially large-scale machine learning problems. And it is invented with the statistical insight that the expectation of the stochastic gradients provide a descent direction. And in this talk, we're going to talk about optimization algorithms powered by statistics that are beyond, the simply taking the mean or expectation. more kind of sophisticated statistical tools can be used in optimization algorithm. So basically, we'll cover 3 different topics, all on using statistics to improve optimization algorithm. The first one is using hypothesis testing for tuning learning rate in deep learning. The second one is variance reduction method for kind of structured non-convex optimization problems. And the second is to use, the third one is to use statistical preconditioning to accelerate optimization algorithms using subsamples. The first one is joint work with my colleagues Pengchuan Zhang and Hunter Lang at MSR, and also Professor Chang Liu from UT Austin. It's about tuning learning rate of deep learning. So deep learning arguably is, I guess, is one, probably the most popular topics in data science these days. So here is a simple example of classifying handwritten digits. So we get input image and go through some convolutional layers, and then also later some fully connected layer, and have 10 output. And this output is compared with a one-hot label through this cross entropy loss function. And the goal of the deep learning is to minimize the total average, say, loss function by optimizing the network weight x. Here, I use x as a network weight. It's you know, the more popular one is using W in machine learning, but here I use x just to be consistent with other part of the talk. And this can be done very kind of easily in PyTorch. You can just, you know, load the training data, and you declare some neural networks, loss function, and here the optimizer is SGD. And then there's a simple loop you can call backpropagation to compute a stochastic gradient, and then the update your weights with some learning rate. Now let's look at the mathematics behind these optimizer steps. So basically, we're solving a stochastic optimization problem, where x is a weight or variables, and k is the random variables data. Of course, in practice, we always have this finite data regime, but here is not that important in our talk. The general form of the algorithm is basically you want to update your variable into a direction d with certain step sizes. So depending on how you take d, there's many different variants. For example, if you take the d as the stochastic gradient itself, you get its classical SGD, and also you can use stochastic heavy ball. Or the Nesterov type of momentum. What's important in practice is really how to tuning the step size alpha k. So in theory, in the stochastic optimization theory, you want the convergence, then asymptotic convergence, you need this alpha k to be this kind of sublinear polynomial decay with some exponent c between half and 1. In practice, this is very hard to tune, and there's lots of adaptive rules for adjusting the learning rates has been developed both in the optimization literature and also the machine learning literature. And also there's an adaptive algorithm with diagonal scaling, such as ADAGRAD, RMS, Prob, and ADAM. But still, tuning the learning rate in practice is kind of art. Let's look at this example. And there's usually two phases of manual tuning. The first, as always, you need to have some trial and error to set a good initial learning rate. And then gradually you want to decrease the learning rate adaptively using different algorithms. And actually, in practice, there's a constant cut algorithm. It works very well. Basically, you, like this on this picture, you know, instead of keeping it constant or kind of decay certain polynomial, then you have this constant, and then you have a drop back factor 10. You know, maybe every 50 epoch or 30 epoch, and then you do this. As you can see, it often has the best kind of both in terms of training and testing accuracy, the right lines. But those good hyperparameters, you know, vary for different model and data set. So So it's very hard to tune in practice. And the work I'm going to present now next is a statistical adaptive stochastic gradient methods. It has like two-phase procedures. The first is, since we do not know the initial learning rate, we'll just start from a very small but nonetheless arbitrary, learning rate. The only guarantee is just small enough, so everything is, nothing blows up. And then we use some kind of a line search procedure to gradually increase it to a certain stable value. Up from there, we switch to a statistical methods, basically use hypothesis testing to see if this process reaches stationarity. And if it is, we will gradually decrease it. So first, I'm going to talk about this statistical procedure first, then we'll come back later, talk about this first stage. So is the reverse order. I will talk this statistical part first. Assume you have a constant, a good initial learning rate. So for this, well, first some few words about why constant cut works. So let's look at some intuition from convex optimization. And when you are in the beginning, when you are far away from the point, the noise is relatively small compared to your gradient information, and then you kind of go into the optimal very quickly. But once you reach this kind of near the optimal point, and then you do lots of random walk. And that's called, you can reach a stationary state there. And in fact, you can write it down as, in the strongly convex case, it will decrease at a geometric rate and up to some floor, C2 alpha. Both the learning rate and the floor are dependent on your learning rate. Yeah, both the convergence rate and the floor convergence. So if you have alpha, the learning rate is large, you get this green one converted very fast, but you settle down a much larger kind of steady state. If your learning rate is very small, then you convert very slowly, but the final accuracy you get is much better. So the best way to do is, use the larger learning rate to reach this kind of higher kind of level of steady state. Then you drop it, keep dropping it, then you tend to kind of more refined state, closer to the optimum. So that's the basic intuition. In fact, there has been lots of rigorous work using statistics from the 50s even to tuning the linear rate of stochastic optimization. And here I list a few of them. You start from check the signs of the inner products. You can do a statistic on that. And also you can check some optimality conditions, then using online t-test. So there's different ways to using t-test also. So I won't go to the details of these things, but just point out there's two key ingredients of hypothesis testing. The first one is what condition do you check for stationarity? And then the second one is how to check them. Now let's go more rigorous and go to a general setting where we just assume this stochastic first order method, where we take actually a more kind of general setting where this direction dk is computed by this kind of a quasi-hyperbolic momentum. If you set up the beta and nu at the proper rate, you will recover SGD, heavy ball, and these sort of the momentum, those kind of things. But the bottom line is that we just assume this simple equation on the top. And we assume that the dynamic will be stable. Basically, the stable linear rate in the beginning is not too large, so you actually stable. The goal is basically how kind of gradually can decrease to smaller linear rate. So mathematically, if you go for kind of the rigorous definition of stationarity, is basically a sequence xk stationary is joint distribution of any subset is invariant shifting, simultaneous shifting in the time index. So in particular, that implies that for any test function, if any test function and any integer I if you evaluate this function at time k plus I and at time k, I mean, you take the expectation, if this pi is a stationary distribution, then they should always the same. So obvious choice is basically the test function is loss function itself. And but this is not directly observable. We can only observe, a single kind of a single mini batch. But nevertheless, it's widely adopted in practice. So basically, that's most people just eyeballing the training loss and then hand-tune their learning rate. That's how they actually are using this kind of a test for stationarity. But it can be formalized with statistical hypothesis testing. But in this talk, we're not going to using this because it has some problems, not as stable. So we are instead using, especially as you can say, it's not a good indicator for yield conditional problem. Basically, it says that even though your weight is still progressing at a very kind of reasonable rate to a certain local minimum, but your loss is already stable, not dropping anymore. So if you use that, you would do prematurely reduce your learning rate. So instead, we use a now there's many conditions you can use, but here we just consider a simple condition. Just use a norm of this weight, all your weights. And of course, you can divide into different layers. So you can do more extension. But basically, the idea is that you just plug in this kind of stationary condition. That means at stationarity, you will have this kind of equation equal to 0. But here, both x, d, those are very easily calculatable at each step. And it's independent of your loss function, independent of your noise model or stochastic gradient. Has nothing to do with that. It always this thing will always hold if the stationarity holds, if you reach the stationarity. And there's other different conditions, special cases for stochastic heavy ball, but these are kind of you can do some kind of algebraic operation that's the or kind of special cases of this simple condition. But notice that here I use dk directly. It does not matter where dk come from. So the statistical test, now we call it SASA, basically statistical adaptive stochastic approximation. Plus is basically the second version of the algorithm. So let's suppose this quantity it goes to 0 at because suppose you're with a fixed learning rate alpha and your stochastic process goes to stationarity. So this we call it the delta k. This quantity is equal to 0. Then by Markov chain central limit theorem, you can say the running average of these quantities go to a normal distribution with certain variance. Now we can do a hypothesis testing. Basically, in hypothesis testing, we always have a down hypothesis and an alternative hypothesis. So the now is basically you assume. So here we just assume the now is stationary, and the alternative is not stationary. So we're going to test if it's stationary or not. We use actually a classical confidence interval test with 1 minus delta confidence. You can calculate the confidence interval as the sample mean and also the kind of a sample variance. But this variance is calculated. I will talk about this sigma hat estimated of the variance of this central limit theorem is quite kind of tricky. But assume we can calculate this sample interval, then we can just do the interval test. Basically, if 0 is not contained in this interval, that means we are far from stationary. So we reject the null hypothesis. And then you keep the learning rate constant. Say things are still moving. Otherwise, you cannot reject now. You are not sure. But then you decrease the learning rate. So that's basically the statistical test we do. Now let's talk about how to calculate the variance estimation. So the most standard way you can do is basically take the sample mean, sample variance as in classical simple statistics. But here, we remember that those are valid for IID random variables. So in a dynamic system like driven by SGD, this delta k is highly correlated. So this formula doesn't work. Instead, we do this, use some Markov chain monocolour variance estimators. It's called the batch mean variance estimator. You suppose we have n samples when divided to a kind of let's see, a p batches. Each one has q. So within each small batch, you can calculate the mean, sample mean, called delta, I bar, and then you do actually the variance calculation on the sample means. It can be shown that this actually has a strong consistency. Basically, when n goes to very large, for example, you can choose p and q by the square root of n, then you will have a consistent estimator of variance. And there's other variations of this estimator as well. Okay, now we got the, I think this is a very interesting subtlety I learned while doing this work for learning some of the Markov chain MCMC variance estimators. They're very, very useful actually for this kind of, essential for this kind of work. So here's the algorithm SASA. It's basically, you have some initial linear rate alpha, and you take the stochastic gradient step. More general, DK you can calculate with different method, momentum, and then you calculate this scalar statistic. Very lightweight storage because it's scalar at each step, and then you just keep the most recent number. We do not keep all the samples. We just keep the most recent n samples, and it's like the once you calculate enough, maybe the last like a quarter example when theta equals 1/4. And then you test it, not every step, not necessary. You can test it every kind of how many steps you can choose. And then you calculate the interval. And if this 0 is within this interval, you will just decrease the linear rate by a factor of tau, is 1/10. And then you reset the, where we keep the samples. So you just keep doing this. A few words on the hyperparameters. There's still, one argument against this work is that you still got many more hyperparameters than the step size alpha k itself, which people only need to worry about alpha k. But now you got this many. But they all have their default values. We can choose in this. But what we want to kind of propose is basically it works actually across different network models and data set, because those values, or you can take from some basic statistical principle, would work for kind of time series, for rule of thumb. They can be adjusted, but it has very low sensitivities. So actually, in all of our experiments are going to present, they all use the same default parameter, even across different model, different data set. So here's let's say the experiments on ResNet on CFR 10. And here's the raw statistic on the left, delta K. And in the middle is the sample mean and the upper lower bound of the interval. As you can see, whenever this thing hit the 0, the interval contains 0, we're going to reset the linear rate. Whenever you reset the linear rate, drop by 10, then the system will become unstationary, dynamic again, then the statistic estimate will shoot up. So during this thing, you still keep this constant. Like this one is more kind of, if you can drop the linear rate by factor of 10, they will take a much longer time to settle down stationary again. And here is some demonstration of the different kind of variance estimators using MCMC. You can see this is very different from the IID estimate. If you use the IID estimator, then you get a very order of magnitude different of the variances. Okay, now we can keep all the other parameters. We can vary the drop factor by drop by half, by by 1/5, 1/10, or you can change the statistic confidence interval. But they all kind of very robust across all data sets. That's why we keep this kind of default setup. And you can try this on other hyperparameters, how many samples you keep, like half or quarter. You can use on different algorithm with this sort of the momentum, heavy ball. They all behave kind of similarly performance. And of course, you can do on ImageNet with similar results. Here, I've just not go into details. So now let's. I've seen that this, given the initial linear rate, we can use this statistical procedure to reduce it. But now we come back to the first stage where you start with a small linear rate and then using a line search. Here this is just review the classical Armijo line search in optimization. You basically go through the direction of decay and you check the reduction in terms of the inner product between the direction and the gradients, and you have some constant, say sufficient decrease constant. And if this one is satisfied, you say, okay, that's a good linear rate, I'll take it. So this is for the smallest case. No, this is called just basically the algorithm. As you can see, still take a sample, take the stochastic gradient, calculate the decay, and each time we'll just increase the step size by 2. And then we'll check this condition on that particular mini batch. Since in the stochastic optimization, we cannot really calculate the function value in expectation. Here we just, whatever the mini batch you have, we just using that to calculate a function and check the sufficient reduction for line search. If it's not satisfied, we just reduce the step size until it's satisfied this condition. And then, actually, this is different from the classical line search. Is this we do not trust this step size because it's on just some small mini batch. That's why we just smooth it with the original one. So gamma will be a number close to 1. That's why you will gradually increase or decrease the linear rate eventually. Okay, now that's the experiment just for the purely the line search. You can start with some kind of tiny linear rate, and then we'll eventually go. Actually, it will just magically stable for the experiment. I think we may not have this, may not expect this kind of behavior for all data set. And I also have to say that here we do not have, this is heuristic. Here we do not have a convergence theorem saying this one will guarantee to be stable. That's still work in progress. But here is just a heuristic. It just works quite well in practice. And then with this heuristic, we combine it with the kind of reduction constant cut kind of heuristic, which done by Statistical here, is that we start the algorithm. There's a switch between them. If it's not switched, then we always run this statistical line search. And then we have some things to check stationarity. We can use the SASA test directly to check stationarity. Remember, the SASA is direct checking for stationarity, so we can use it here. And for safeguard, this the reason we were using a heuristic, as I said. We have a slope test. This is the object function is not actually growing, obviously, not exploding. And then if any of the indicators shows that it's stationary, then we switch to the SASA, which is basically, as you said before, it just drops stationary until it finally converges. So that's a whole implemented algorithm. Here again, we show some experiment on CIFAR10 and ImageNet. Here you can see the linear rate changes. There's different kind of constant cut tunings, and this one is like the red one is combined algorithm. Start with a tiny one, just increase, and then it will just decrease by itself. All done automatically. And we can use the same parameter on convex problems or on some RNN. They all behave reasonably well. May not be best. The more experiment we do, we realize not as perfect. So, but this is certainly an interesting direction to go. Okay, now let's summarize SALSA. Basically, it's an automated two-phase procedure. The first stage we warm up with some smooth line search. to make it the learning to reach certain stable state. And then from there, we will just gradually decrease the learning rate based on statistical test. You can view the first stage to reach some sufficient exploration, and then the second stage just to come down, to convert to a good local minimum. But we do not, other than the SASA part, we have this kind of statistical test theory. We are not proving, the more precise convergence theories of these algorithms. I think there's still lots of work to do. So in general, I think statistical hypothesis testing is a very powerful tool for stochastic optimization. I mean, basically, you can make lots of intuitions more rigorous and more powerful, and help make training machine learning models more autonomous and reliable. In fact, here I put a quote from Rosinsky and Siski in '83. They said, the speed of convergence of questions are closely related to online rules for determining steps coefficient in stochastic approximation algorithms. In the author's opinion, the use of statistical tests is a very promising direction of future research. So this is like almost 40 years ago. But I think now we have shown that this really can be very promising. Okay, let's pause a little bit because this is the first topic about using statistical hypothesis testing to tune in the learning rate. Now I'm gonna switch in gear to the second part. So the last two parts are gonna is much shorter. Just an overview. I won't go to too much details of this. The next one is the variance reduction for composite optimization. This is joint work with Junyu Zhang, who is PhD, finishing PhD in University of Minnesota, moving to Princeton as postdoc. So let's recap some finite-sum optimization. I think it has been very popular in recent years. And the classical SGD, as I've shown here, the problem people discovered that the problem with this, you have to reduce alpha k go to 0 is because the variance of gradient actually is not going to 0 because it's stochastic gradient. And if you want to convert to some station point, you have to control the overall variance going down. You have to using the step size to make it converge. But there's practical implications because the first one is, as we just talked about before, it's hard to tune alpha k to go to 0 in practice. Now, how fast do you reduce it? And also, it's very hard to work with L1 regularization because if you want to sparsely in your structure, then your kind of self-thresholding will decrease to 0. Actually, you will no longer getting a kind of sparse solution. Another one is that the convergence usually is slow, but I think this is probably the least worry for practitioners. So variance reduction actually is a technique capable to improving all three aspects. Let me just give a simple recap of variance reduction with control variate. So the goal is, I suppose we want to estimate the mean on the random variable x with low variance. And the control variate basically is another random variable y such that its expectation very easy to compute. And also the difference can be sampled, estimated with roughly the same cost as x. That do not encounter much more kind of cost in sampling. And the variance of the difference is much smaller than the x. So if you have this control variable like this, then you can define x prime, which is basically the difference corrected by the expectation of y. And then actually satisfies they have the same expectation, which is much smaller mean. So that's basically principles of variance reduction in statistics. For SGD, what we do is basically, this is a stochastic gradient, and your control variate is actually a y is actually a stochastic gradient at a fixed point. And its mean takes a lot of time to compute, but often you can just compute it once. You don't have to move this x0 as often as k. So if you can see that if x0 and k are small, the distance is small, then the variance will go down, and you will ensure that the variance of this stochastic variance reduced gradient goes to 0, and then you can actually use a constant learning rate. Once you use a constant learning rate, then all the three aspects I mentioned in the previous page will actually get improved. So for stochastic variance reduction, I just here show one of the early ones as SVRG, and it's done in stages. So at the beginning of each stage, you calculate the stochastic gradient, the full gradient at x0. And then you will take a stochastic gradient steps using this variance reduction technique. After m steps, you will reset the initial point, recalculate it, goes on. And of course, a assumption that's critical in this kind of technique to work is that your gradient has to be Lipschitz continuous. That's the whole point, to argue that when the 2 points are closer enough, then your variance also goes down. In fact, you can see the complexities of if you want to reach in expectation error epsilon, that's the complexity of different kind of algorithms. There's a classical gradient descent, SGD, and SVRG. This is all well known. And of course, in the non-convex case, interestingly, actually, they are worse for the variance reduction techniques. But there are also recent variants. Basically, say like a SARA and Spatter, basically say you do not, keep using the V0, but each time you will update your kind of control variate itself. So this lead to a kind of much more improved results. For the convex, non-convex case. For convex, they're basically the same. Okay, now this is a recap. Now I'm just going to discuss some of the recent work we have done on composite stochastic composition. Basically, you can consider, there's a composition outside the expectation of Finite-sum. And this composition also need to be smooth. All the mapping are smooth. There's lots of applications in kind of policy evaluation, or actually this example, for example, risk averse optimization. You want to kind of minimize average reward. HJX is basically some kind of reward. You take the average, and this part is basically the variance. And this will give to this kind of composite form. There's lots of application. And also you can consider kind of multiple levels, of either expected or Finite-sum. And so the basic result is basically that the dependence on epsilon and the total number of functions n is very similar to the one level case. And depending on the number of levels, m is polynomial. So that's basic result. I will not go into any details. Just show that the variance reduction techniques of Spatter or SARA in this case we're using can be extended to multi-level compositions. The basic principles are similar. You just need to go through bound the gradient variance after you take the chain rules. So that's the result. Another more interesting variance is basically when your composition function f is non-smooth. So this is interesting because, as we have seen before, smoothness is critical in this kind of variance reduction. But if you can take the approximate map of f instead of taking the gradient, then things can be better. That's what we have been working on this one. If f is convex but maybe non-smooth. There's examples for distribution robust optimization, but I will skip this example. But I would like to take a more kind of interesting example where SGD, with better model. So classical SGD basically say, you take any kind of mini batch and you linearize the loss function. You put as a graduate a penalty. So a truncated SGD basically say, I recognize, this is a better model because in lots of machine learning problems, the loss cannot be less than 0. Then you say you just put the truncation, this is a more sophisticated model, but it's non-smooth. and then you do a stochastic. You can do a stochastic gradient on this. It has been shown that it has a kind of closed form solution. It has a lot of kind of advantages than the kind of classical SGD. But here, the analysis naturally falls into the one where it's a composition with a non-smooth composition, but you can take a kind of approximate map is easy to compute. And for this kind of problem, we basically say, we can again use variance reduction. We call it variance reduced approximate linear algorithm. You basically replace the linearization inside the composition with different estimators, variance reduction measures, and then you can get some improvement. But the improvement, of course, is worse than the smooth case. But it does, can give you some improvement. It's a little bit surprising. Okay, of course, you can do also QB regularization, just to make sure that you have this second order guarantees on your local minimum. And this is a famous work by Nisrov Polyak. And the sample complexity basically has the 1 epsilon kind of 3 halves, negative 3 halves. And then at each step, you need to sample n hashings. But then we can show that using variance reduced estimators, you can make this down to into the two-thirds. So basically, now I have showed you kind of the variance reduction technique, is a very fundamental principle in statistics, can be used to improve across board a lot of optimization algorithms with different composition, different structures. So that's this second part. For the next part, I will talk to the last part of statistical kind of optimization method is called statistical preconditioning. This is joint work with Adrian Hendricks, Sebastian Bobek, Francis Bach, and Laurent Masuri. Sebastian is a colleague at MSRAI, and then the others are actually from INRAM, France. So now we actually come back to the more kind of simpler model, which is convex. We assume convex losses, loss function L, can be least squares or least regression. I don't know if you can see my screen.
Yes, we can see your screen.
Oh, my screen maybe died. I just suddenly cannot see my screen. Maybe the HDMI has. Okay, I don't know how this is going to work because I completely lost my computer screen.
Maybe you can try to redo the screen sharing or.
No, I cannot basically see anything about the screen. Maybe it's hardware issue. Okay, but can you see my shared screen?
Currently, I can see your slide 37, the motivation slide.
Okay, maybe I just talk in the blind. So you tell me which page I'm on. Okay.
Maybe you can send us the slide and we can let the.
No, I cannot see I think my local computer hardware. I cannot see screen at all.
So you mean you cannot see anything? So
yeah. So it's my local computer's problem. But somehow I can talk. Let's go through. Okay. So long as you can see it.
So now it's motivation. So how about Jordan? So whenever Dr. Xiao go to a new slide, you just tell him the title.
Yeah, that help. If I'm just moving the mouse.
Okay.
So this is still the first half, okay? So you see the second half? is about the motivation for distributed opposition.
No, we only see the first half.
Okay, now.
Maybe this means that the screen is frozen.
Yeah, I apologize. I don't know. This is the first time happened to me. I suddenly lost completed.
How about you restart the computer? We can wait for a few minutes.
Okay, let me do that.
Yeah, so audience, please just wait for a few minutes.
Okay, I'm coming back. Do you see?
Yeah.
Yes.
Okay.
Yes.
I'm thinking the problem was the HDMI cable on my computer, but sorry about that. Luckily, we can still go on.
Mm-hmm.
Okay. So here we consider the very large kind of scale where you need a distributed computing. The data cannot fit in a single machine, and each machine we can have like n samples, totals m times n. But we want kind of a communication efficient distributed algorithms for solving this. Here is the most basic algorithm everyone can think about and go ahead and do it. Basically, you just have a server just broadcast the current state xk, and then all the other machines compute the local gradient and send it back. And the server can just take the gradient step. For this talk, we also assume this is strong convexity, which is kind of actually reasonable because you almost always have some kind of a regularization. And so the number of communication in this case is actually the same as the number of iterations of the gradient algorithms. You can have, condition number kappa times log 1 epsilon, or using accelerated gradient methods at the local machine, the server. Does not cost anything more in communication. You get this square root of kappa. In general, this actually cannot be improved if you do not have additional structure in the local functions. So here's better explanation of the condition number. Basically, the upper lower bound on your hashing the largest smallest eigenvalues. If their differences, the ratio is large, then you get this kind of bad situation of more iteration needed. And the preconditioning basically is the computational efficient schemes to reduce the condition number. So in order to do explain preconditioning, we'll actually talk about preconditioning from a more general perspective of relative condition number. So here we first define the reference function phi, which is differentiable and strongly convex. We have the lower upper bound on the hashings. You can define the condition number yourself with all subscript phi. And then we say a function is, capital F is relatively smooth and relatively strongly convex with respect to phi. Is their hashing satisfy these kind of conditions for every point x in the domain. So here I use this kind of F over phi as a relative notation. So you can define actually the relative condition number in this way. And alternatively, you can define the Bregman divergence using this reference function. And the equivalent to say the Bregman divergence is kind of upper lower bounded in the similar ways. So now let's talk about precondition gradient or proximal gradient methods. So basically, in the classical gradient method, you will see this part as a kind of quadratic difference, quadratic distance squared. And we just replaced by a general Bregman divergence. And you can show that you have the convergence rate similar to the gradient method, but you just replace a condition number with this relative condition number. Now here come back distributed opposition. suppose you have like M kind of different machines, each one has their local data. And here at the server, we just use the local function plus some kind of a regularization mu to do the regularization. Extra regularization, actually, that's the thing. If you do that, let's analyze what's the relative condition number. So the simple lemma can show that if the a spectral bound of the difference of the two hashes is less than mu, then the hashing satisfies this condition. Now you apply the concentration bound with this, because this local function itself is sampled from n data set. And you can get this kind of a spectral bound with a metric coefficient, and then you get the mu is basically one scaled at 1 over square root n. Now you can just define the relative condition number, calculate the relative condition number easily with 1 over square root n. So when n is large, this will be smaller than original condition number. But there's some caveat. Basically, we need this kind of concentration bound to hold for all x in the domain with high probability. Basically, this one, this red star equation. So for quadratic, this is not a problem, and we can easily give a conclusion of this kind of relative condition number. But for non-quadratic, we need some kind of a more ball packing uni bound will encounter you a square root dimension factor, basically said that the benefits of preconditioning may degrade in high dimension. So this is really bad because D can be very large in applications. So I'm just go directly to the result we have. One is we have a kind of a preconditioned accelerated gradient method, which is almost accelerated. You can see this is 1 over square root kappa, relative condition number. So this part is independent of the condition number, basically acceleration, with some kind of a small overhead, which will disappear in practice. So empirically, you will get this kind of square root of the relative condition number convergence. This is actually not an easy result because theoretically, acceleration in the relatively small strong convex setting is difficult, and there's recently some negative result about it. So in this case, we can actually get this kind of result, although still not perfect. But because we assume phi itself is strongly convex in the Euclidean norm. So that's basically. For the second result, which is basically independent of this acceleration, is improves the statistical preconditioning. In fact, if we focus on the linear prediction model in this form, like logistic regression, and then for quadratic or least squares, we can actually improve the factor by square root n. You get a 1 over n scaling of the condition number. And for n is your local number of samples. For non-quadratic, actually we can remove the dependence on the dimension. So this is, I think, is more kind of stronger improvement theoretically. So this is relatively independent because you can use this bound to directly improve any kind of a gradient or accelerated gradient method you can use across the board. So these two kind of relatively independent results, they will complement each other. So this is a typical, I will skip this. I mean, it's more like an accelerated gradient algorithm people have often seen for this type of acceleration. I will skip the details here. Yeah, just give you some, actually for the time consideration, I'll just show you that this kind of acceleration, if you use this picture, you have some kind of a, RCV1 now considered small data set. You can have the reasonable kind of a KDD 2010, like 20 million dimension, like 7 million samples. Like I think this one is for like 16 machines, and the regularization L2 is actually 10 to the -7. It's tiny. You have a huge kind of bad condition number. But we take like 10 iterations, 20 iterations. You get like almost 10-digit accuracy, which is unnecessary in practice anyway, but just shows you how powerful this kind of technique is. Okay, now let's actually, let me just summarize everything. So I have covered 3 kind of different works, which all in the spirit of statistical optimization methods, basically optimization method that's powered by statistics, hypothesis testing, variance reduction, and preconditioning. There's other recent work we have done on just using proximal boosting to obtain high probability stochastic optimization. Because in lots of the standard stochastic optimization, stochastic gradient literature, we only see convergence in expectation. And for any kind of high probability bound, you need to assume some kind of a light tail assumption on the noise. But this work, we just use some proximal boosting technology, just get high probability bound without assuming light tail noise. So that's also a pretty powerful kind of a technique using statistics to boost optimization algorithms. In general, I think this, as we are working in the big data or data science era, I think randomized algorithms, stochastic algorithms, can be much more powerful if paired with statistical methods. More sophisticated statistical methods you can do kind of achieve much more than the purely separated optimization algorithm. Okay, thank you. That's all my talk.
Okay, thank you, Dr. Xiao, for the great talk. And let's look at the questions. The first question is from Jie Wang, and he's asking, he or she is asking, how to choose the sample size n to ensure the asymptotic convergence for CLT is valid. I think maybe he's talking about the convergence rate of the CLT. In practice, how to ensure that you have a sufficient large n to ensure that CLT is valid.
Yeah. So that's just 2 answers. One is in practice, we just take the, let's say the last quarter samples. If you sample like 1,000, so that could be like a 500, those kind of things. But it's keep growing. So if that depends on the test. So the test, if the test is not satisfied, the sample will keep accumulate sample until it's satisfied that's interval test. Of course, here is kind of heuristic. We just look at this. In practice, this quarter sample will be working enough. On the other hand, suppose each time you tune the rendering rate, when you're getting closer, if you change the rendering rate, then your disturbance to the stationarity become weaker and weaker. That means somehow this statistical test always satisfied in a reasonable time. So we do not, as I said in the beginning, we do not have rigorous theories about this thing will converge. Actually, how fast it convergence rate. We just use the kind of the basic principles of statistics to say this will be a good method in practice. And I think there's lots of theoretical questions and to be answered.
Thank you. And another question is also from Jie Wang, and the question is that the stationary? It seems that the stationary condition might depend on the smoothness of the target function phi. Is there any guidance for non-smooth functions? For example, we might use ReLU activation in the neural network training.
Well, this is not, the phi is not kind of related to any kind of ReLU or activation function. The phi is arbitrary. You can basically use, so for here, as I said, you can, if the distribution of the random variable are the same, then you basically, if you take any function, you get the same. You should have the same. So here is basically for your convenience. We just say, here we choose basically the most intuitive thing. We just observe the normal, the total weight is not, when it's not changing, then we say, okay, more likely it's stationary. You can use a much more sophisticated variant. For example, you can check the weight of each layer to make sure, then you can say it's a better condition for stationarity. I agree, there's so many different choices you can do. We just use probably the simplest you can check.
Thank you. And another question is from Yibo Zhang, and the question is that the learning rate tuning techniques aim to converge fast on training loss, and he or she is wondering, how do you see the potential effect on the generation phenomenon for neural networks? That is the testing accuracy. For example, with different learning rates, the algorithm might find different local minimum, and which might lead to different testing accuracy.
Yes. So this work, again, we do not cover those. As you can see, this kind of our statistical test is basically mimic the constant and cut. You know, every people use constant cut in practice. It seems to be that if you just tune the constant cut parameter right, you actually get better generalization in practice than even Adam or other things, right? And that's what people kind of widely accepted one kind of trick. So then our kind of statistical procedure basically can consider as a way to automate tuning of this constant cut scheme. So we do not really address the capability of generalization or even a better stationary point, local minimum. I think we do not address anything on those.
Mm-hmm. Thank you. And another question is from Hongpeng Sun, and the question is, for the cubic regularization Newton method, could you please give some comments on how to solve the large linear system for the stochastic Newton method?
Yeah, that's that one. I think is a more very kind of a theoretical interest. See how much sample you need, and as you mentioned, end of the day, it has the same. If you want to save the subsystem in the cubic regularization, end of the day, you have the same dimension size of matrices or algebra needed. There you can there it is possible if you can explore some low rank. If your sample size is small enough, you relatively small, you can explore those kind of things. But I doubt in practice this will have some significant difference. So I would just say that is many of that work is many of theoretical kind of results saying that in terms of sample complexity of the Hessian, you don't have to use all the samples. You can use like into the 2/3. But in practice, I think I agree. There's lots of things if you really want to use the cubic regularization techniques.
Mm-hmm. Thank you. And another question is regarding on the implementation of the algorithm. For the first part of the talk, in practice, how frequently do we need to conduct the hypothesis test for convergence when running the algorithm? And when we conduct multiple tests, and these tests seem to be correlated, and do we need to adjust the p-values of these tests?
Yeah, those are, I mean, that's a great question. You know, to be honest, we do not have any kind of rigorous answer. Okay, but like I said, in the end of that part is basically, we hope to raise the kind of awareness of this kind of statistical techniques. And to answer your question partially, yes, it's kind of the, if you do tests repeatedly, in practice, we basically test, 100 some iterations, we just test one. It doesn't matter, it's just 200. So what matters is actually the how many samples eventually will accumulate to make the test true or false, detect it. Because for testing the test is computationally completely can be ignored. I mean, it's just like thousands of scalars, you calculate the mean. It's a variance. That's not a burden at all. You can test as frequent as you want or less frequent, but that's not a big deal in practice. And also, if you look at the curve, we showed the interval is actually the monotone decreasing to hit the zero. So this is much easier if you see kind of what is it called in statistics is repeated testing on this thing will be a trouble if your quantity is always near zero, and then there can be some kind of theoretical issues. But in our case, at least in practice, we observe the quantity is always monotonically approaching 0. So that's less kind of a concern from theoretical side. But still, agree, there's also things, all are valid questions that should be addressed more rigorously.
Mm-hmm. Thank you. And the last question is from Thomas. It's it seems a explanatory question. He is asking about SASA plus, the algorithm SASA plus, and it seems that you test the stationarity by testing the hypothesis if the mean of the process, the algorithm process stays constant by computing a confidence interval for the mean under the assumption of a normal distribution.
Yeah.
And he's asking whether this understanding is correct.
Yeah, this, let me actually go back to that part. So it's this, right? Basically this.
Yeah.
Yeah, I think we just take the, I think most, if you agree, we will just take the most kind of, you can see the vanilla version of this central limit theorem with all the regular assumptions which it could hold. Mm-hmm. So that's whether or not it's really a Gaussian or how this variance changes. I think there are actually, especially in the deep learning case, is a nonlinearity, non-convexity. There are lots of issues there.
Mm-hmm. Thank you. And Thomas also follows up that there are other hypothesis tests that are non-parametric for change point detection in time series. So he's asking whether it's possible to incorporate those hypothesis tests in the algorithm.
I do not know those kind of techniques, but in general, I would say why not to try? I mean, if you for this basically this whole work, we just show that here we see statistical test is not some kind of a very kind of say special technique can handle linear rate tuning. That's not the starting point. The starting point that we have a lot of intuitions like about experience how to tune this linear rate by observing different signals, and lots of time we based on hand tuning. But the goal is here is basically we try to come up with ways to automate this process, just to make your intuitions kind of more easily automated. That's why we borrow the statistical test machinery to help us to automate this kind of your intuition, like the constant cost game. How do you not need to tune it by yourself on each different data set or models? So that's the kind of motivation for this work. And of course, if you think any kind of other statistical techniques are kind of useful to help you to automate your intuition, get better empirical process results. I mean, I think it should be, just try it. Should be.
Thank you, Dr. Xiao again for the great talk. I think it's about the time, and also thank you very much for attending today. And we are looking forward to seeing you guys on this Friday in the 11 a.m. Eastern time.
Okay, yeah, thank you for